All right, hello everyone. We're going to go ahead and finish up the second half of the slides for part 2 of Standard 4. Part 1 focused on vertical asymptotes and how they can be defined by infinite limits. An infinite limit is where a function increases or decreases without bound as x approaches some constant from either the left and the right. If it increases or decreases without bound, the function will approach either infinity or negative infinity and therefore create a vertical asymptote for our function. Now what we're going to do next is look at horizontal asymptotes and how they can be defined by not infinite limits, but what are called limits at infinity. That definition is given down here in this line of text. The horizontal line y equal L is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of function f of x is equal to L, or if the limit as x approaches infinity of f of x is also equal to L. So let's see how this is different from the previous one. In our previous notes, we had infinite limits. So as x approached some constant, my function had the unbounded behavior and either approached positive infinity or negative infinity. Now I have the exact opposite. Rather than x approaching some constant, now it's approaching either negative infinity or positive infinity, and it's the function itself that's out towards some constant. It's just switched around. So let's look at this picture of the function down below. As x goes to negative infinity, as I go down and to the left in this graph here, the function has a behavior to tend to be equal to 3. So in terms of a limit at infinity, the limit as x approaches negative infinity of our function f of x is equal to 3. Rather than the limit of x approaching 3 being equal to negative infinity, now it's the limit as x approaches negative infinity being equal to 3. Vice versa, as x approaches positive infinity, as the x values increase without bound, the function also approaches 3 as it gets closer and closer to 3 as x gets larger and larger and larger. So in terms of a limit at infinity, the limit as x approaches positive infinity of our function f of x is equal to 3. Because each of these two things are true, my function has a horizontal asymptote at the horizontal line y equals 3. All right, let's look at a couple of helpful limits at infinity before we evaluate these limits by hand in a second. So first off, the limit as x approaches positive or negative infinity of some constant b will always be equal to b, because b is independent of whatever it is that x is doing. Because it's independent of x, whatever x is approaching does not affect that constant. So for example, if the function f of x equals 2, if I take that limit at infinity, as x increases without bound, we're always equal to 2. As x goes to the left and decreases without bound, we're always equal to 2, because the function's defined that way. It's defined to be equal to 2 no matter what x it is. So in the general case, the limit of any constant is always equal to that constant. Now in part 2 here, what if I have the limit as x approaches infinity or negative infinity of that constant b divided by some power function of x? Well, if I have a constant divided by x to the r, and x is getting bigger and bigger and bigger and bigger, I take that constant divided by a really big number. Something divided by a really big number is going to get to 0 pretty quickly. So what if I had 2 divided by x to the 4th? I have the constant 2 divided by x to some power, a power function of x. as x goes to the right, as it increases without bound, I get closer and closer to 0 pretty quickly. Same thing as it goes to the left. As I go to the left, as x decreases without bound, as it gets smaller and smaller and smaller, I get closer to 0 pretty quickly. Any constant divided by x, as x becomes infinite, will become 0. Okay, so let's go ahead and find each of these limits here on this tab. What's the limit as x approaches infinity of 5 minus 2 over x squared? Well, let's take this one at a time, term by term. What's the limit of 5 as x goes to infinity? Well, as we know from the previous slide, the limit as x goes to infinity of any constant will always be that constant. So in this case, that first term produces 5 as I take the limit. Now the second term, 2 over x squared, as x goes to infinity, if I have some constant divided by a power function of x, that's going to be 0. 5 minus 0 is 5. Now you can always confirm this using a graph. As x gets arbitrarily big or arbitrarily small, we get closer and closer to 5. In part B, or part 2, we had 2x minus 1 divided by x plus 1. Okay, now I have a rational function, 2x minus 1 divided by x plus 1. One kind of algebraic tool that's helpful here is I'm going to divide the top and bottom by the same thing. I'm going to divide by the largest power of x. The largest power of x in the numerator is x to the first, same thing in the denominator. So we're going to divide every single term by x. So when I take 2x divided by x, minus 1 divided by x, x divided by x, minus 1 divided by x, that's going to give me 2 minus 1 over x divided by 1 minus 1 over x. And it looks a lot like what we had up in part A on both the top and bottom. Take the limit as x approaches infinity of each of these terms. 2 minus 1 over x, that will be 2 minus 0. Divided by 1 minus 1 over x, 1 minus 0. That's 2 divided by 1, or 2. As x approaches infinity, as x gets arbitrarily bigger and bigger and bigger, infinitely bigger and bigger, my function is going to get closer and closer and closer to 2. All right, part 3, we have lots of very similar looking functions to take the limit as x approaches infinity. 2x 5 over 3x squared plus 1. Part B, 2x squared plus 5 divided by 3x squared plus 1. And part C, 2x cubed plus 5 over 3x squared plus 1. What I want to look at is how the powers on 2x affect my answer. Notice that the bottom, the denominator, remains the same. It's always 3x squared plus 1. But I'm taking the degree of the numerator from 1 to 2 to 3. So for our first one, the limit as x approaches infinity of 2x plus 5 divided by 3x squared plus 1. So what's the largest power of x? Well, obviously that's going to be x squared. So we're going to divide everything by x squared. 2x divided by x squared plus 5 divided by x squared over 3x squared divided by x squared plus 1 divided by x squared. That's going to give me 2 over x plus 5 divided by x squared divided by 3 plus 1 over x squared. When I take the limit as x approaches infinity of the top, I'll get 0 plus 0 divided by 3 plus 0. That's 0 divided by 3, which is 0. As x approaches infinity, this function tends to be equal to 0 pretty quickly. Now, let me erase this here. Just to save some space. And let's see what happens when I change it from 2x plus 5 to 2x squared plus 5. Since x squared is still the largest power, what we need to do is divide each of these by x squared. So we'll have 2x squared divided by x squared plus 5 divided by x squared divided by 3x squared over x squared plus 1 divided by x squared. When I simplify each of these, we'll get 2 plus 5 over x squared divided by 3 plus 1 over x squared. When I take the limit of term by term, 2 plus 0 divided by 3 plus 0. Any constant remains constant. Any constant divided by a power function of x as x goes to infinity goes to 0. So now my function is going to approach 2/3, or approximately 0.667, as x gets infinitely larger and larger and larger. Okay, let's look at one more example. I'm going to change x squared to x cubed. Now, because x cubed beats x squared, we're going to divide everything by x cubed. So 2x cubed divided by x cubed plus 5 divided by x cubed divided by 3x squared divided by x cubed plus 1 divided by x cubed, which is going to give me, when I simplify, 2 plus 5 over x cubed divided by 3, I'm sorry, So that's going to give me 3 over x plus 1 over x cubed. When I take the limit of term by term by term, I'm going to get 2 plus 0 divided by 0 plus 0. And so we can see that this function is going to be undefined because when I divide by 0 plus 0, it's undefined. So how do I take this limit as x approaches infinity? Well, let's look at our power ratios on top and bottom. I have a cubic function in the numerator and a quadratic function in the denominator. Which of those is going to get bigger faster? Well, since cubic beats quadratic, the numerator is going to increase faster than the denominator. So as x gets larger and larger and larger, that difference in rates is going to make the top increase faster than the bottom, and it's going to increase that difference between the two. So eventually you're going to have a really, really large number divided by a really, really small number, and that would be infinity. So this case kind of fails. So what we have to do is look at kind of that ratio of powers. In this case, I have a large positive number divided by a smaller positive number. As x goes to infinity, that difference is going to increase exponentially, and we're going to have a limit at infinity being an infinite limit. So let's look at this case. I had cubed. Notice as x gets larger and larger, the function gets larger and larger. It increases without bound because cubic increases faster than quadratic. So over time, I'll have a larger number divided by a smaller number. As x increases, that difference also increases, and eventually we'll have an infinite limit for this limit at infinity. Instead of 3x squared plus 1, what if I had negative 3x squared plus 1? Notice now I'm going to have a positive number divided by a negative number, so this would be equal to, as x goes to infinity, now it'd be equal to negative infinity. This limit at infinity would be negative infinity. All right, a little bit here on kind of some shortcuts that I notice. Let's look at part A. I want to find the horizontal asymptotes of each function. I've got a linear function on top, a linear function on bottom, so they're going to approach infinity at the same rate. When that's the case, look at your ratio of leading coefficients. The leading coefficient in the numerator would be negative 1. And the denominator, leading coefficient, would be 4. So y equals negative 1/4 would be our horizontal asymptote. I have negative 1 divided by 4. For part B, take the limit as x approaches infinity. 1 minus 2 over x squared. The limit of 1 is 1, 2 over x squared is 0. We'll have a horizontal asymptote at y equal 1. For part C, now I have x divided by x squared plus 1. As x gets larger and larger and larger, what gets bigger faster? We'll have a linear function and a quadratic function. Since the quadratic function gets bigger faster and it's in the denominator, I'm going to be dividing by a larger and larger and larger number. When that happens, I get smaller and smaller and smaller, and eventually I'll have a horizontal asymptote at y equals 0. In part D, notice that now I have a cubic function on top and a linear function on bottom. When the degree is larger in the numerator, it's going to get bigger faster than the denominator. So I'm going to take a bigger number divided by a smaller number. That difference is going to increase as x goes to infinity. So I'm going to take a larger number divided by a smaller number. That's going to become infinity as x approaches infinity. So I don't approach a number as I take this limit. So in this case, there is no horizontal asymptotes. Degrees equal, look at the leading coefficients. Bigger on bottom. Bigger on bottom, you're going to have the denominator getting bigger faster, so you're dividing by a larger and larger number. That'll get closer and closer to 0. For part D, we had no horizontal asymptote because now the top is getting bigger faster. On part B, it wasn't a rational function, but I just took it term by term. All right, so that should be the last slides here for standard 4. I think we'll call it there. See you next time, guys.